Hello everyone, today we will be learning about standard reduction potentials, which is the third section of galvanic cells. Let us begin. First we will be learning about EMF. EMF is given by this symbol here and it's measured in volts. It stands for electromotive force and it is the same as voltage. So voltage and electromotive force or EMF are the same thing. The EMF is the difference in the reduction potentials between two electrodes making up the galvanic cell. So for example, copper and zinc in a Daniell cell will have two different reduction potentials, and the difference in those reduction potentials will be the EMF of that cell. The reduction potential is the ability or the tendency of an element to undergo reduction. So the lower the reduction potential, the more tendency it is going to be oxidized, and vice versa. Standard reduction potential. This cannot be measured by itself. It requires two different half cells to generate a measurable EMF. And also it is measured against a standard hydrogen electrode as a reference. So if you look at your standard potential table in the back of your periodic table, you would realize that hydrogen has an EMF of 0. That's because it is compared against 2. Now let's take this one for example. We have hydrogen. This is a standard hydrogen electrode. So using hydrogen ions with hydrogen gas as a common or reference electrode. As you can see, we're using a platinum electrode coated with platinum black, and that's this electrode here. Because we're using a gas, we have to use an inert electrode, and we're adding hydrogen ions in, and it's going to be 1 moles per liter, and this is happening at 1 atmospheric pressure and also at 25 degrees Celsius, which is room temperature. The platinum black is a fine powder of platinum with excellent catalytic properties, coated in the platinum electrode to increase the surface area of the electrode, giving it superior catalytic properties. Because it's increasing the surface area of the electrode, it is increasing the efficiency of the reaction. And that is why we use platinum black to coat on the platinum electrode. This is the reaction that is undergoing in that cell there. We have the hydrogen ions reacting with the electrons here. So it's gaining electrons to form hydrogen gas, and hydrogen gas is given off. With the reduction potentials, they're measured under standard conditions. And as you can remember before, we use 1 atm, 25 degrees Celsius, and also 1 moles per liter concentration of the hydrogen ions. And those are the conditions. And the designated symbol for EMF is this, or EH. But this is much more commonly used, and you will see it more in HSC papers than these. So the standard conditions is the electrolyte solution. It has to be 1 mole per liter. So both of your electrolyte solutions have to be 1 mole per liter to have standard conditions. The gas pressure has to be 1 atomic atm. So for example, the example we took before has 1 atm as gas pressure. And the temperature has to be room temperature, that is 25 degrees Celsius. And hydrogen half cell against the EMF. So these are the 4 standard conditions which you have to have in a galvanic cell. Now moving on, we have the table of some standard reduction potentials. You would have the full table in the back of your periodic table, and we're just looking at some here. We have sodium, magnesium, zinc, hydrogen, silver and chlorine. So if you move up the list, the reactivity of the metals increase. So the reactivity increases as we move up the list. So sodium is more reactive than magnesium, for instance. Hence, the elements at the top tend to reduce species lower in the table. That means these species undergo oxidation while these species undergo reduction. The reactants found at the bottom of the list are nonmetals and transitional metals. For example, chlorine is a nonmetal and silver is a transitional metal. They are strong oxidizing agents, which means that they undergo reduction. So oxidizing agent means that they undergo reduction. The products found at the top of the list are reactive metals, which means, for example, sodium is a very reactive metal, and they are strong reducing agents. Calculating the cell voltage. So in your HSC, you would be asked to calculate cell voltages after writing the reduction reaction and the oxidation reaction. And you can do it by using this formula here. We have the EMF, which equals the EMF of the cathode minus the EMF of the anode. Now we'll take the Daniell cell for an example. We have oxidation. The oxidation is a zinc losing electrons to form zinc ions, and the EMF is 0.76 volts. Now to find the EMF, you turn to the standard potentials table in the back of your periodic table, and you would see that it has 0.76 next to the reaction. And here we have reduction, which is copper ions gaining 2 electrons to form copper, and the EMF is 0.34 volts. The EMF is obtained from the table of standard reduction potentials, as I mentioned before. Cell potentials is a sum of the oxidation potential and the reduction potential. So if we take a look at how they work it out, we have zinc. This is the overall reaction, zinc plus the copper ions producing zinc ions and copper metal. Here we have 0.34, which is for the copper, and then we have 0.76, which is for the zinc. But realize that there is a minus here, and that is because in the standard potentials table, the equation is the other way. So when we are writing it down, we have to change the sign to make it correct. And if we do the sum, we will have 0.34 minus, brackets open, minus 0.76, which would make this a plus, and sum it up to get 1.1 volts. Now note that the sum is a positive integer. However, it may not be a positive integer in some cases, and these cases are called electrolytic cells. Now, a positive cell potential indicates that the reaction occurs spontaneously. That means without any energy input, it happens. And that happens in galvanic cells, which we were learning before. But it's a different case in electrolytic cells. In electrolytic cells, a negative cell potential is happening because energy input is required for the reaction to take place. And that is why we have a negative cell potential there. Now this wraps up our lesson for today. However, we will be looking at some questions. We learned about how we calculate EMF and also what EMF is. So let's take a look at some questions now. Question number 9. We have a multiple choice question here. What would be a suitable electrolyte solution? So we have 4 options here, and this is the example that we're referring to. Is it A, hydrogen gas dissolved in water? Hydrogen gas dissolved in water does not conduct, so option A is not the correct answer. Is it option B, which is solution of a platinum salt? We know that platinum is an inert metal, so that is not the correct answer. Option C, which is solution containing 1 mole per liter of sodium chloride solution. Now we know that there are hydrogen plus atoms, plus ions in the solution, as you can see there. So that is not the answer. The answer is option D, because solution containing 0.01 moles per liter of hydrogen ions. So that is the answer, because reacting the species in the electrolyte is a part of the standard condition, and that is the answer. Now let's move on to question 10. Question 10 is a multiple choice question as well again. The redox table is a list of standard reduction potentials. Use the redox table to determine the correct oxidation reaction for copper. Now you would have to refer to your standard potentials table, and we have 4 options here again. Option A, it has copper gaining 2 electrons to give copper, the solid. Oxidization is losing of electrons. In this case, we're gaining electrons, therefore that answer is incorrect. Now let's consider option C. Option C has calcium gaining electrons to form calcium, the solid, the metal. But again, we're talking about copper, not calcium. And further, oxidation is the losing of electrons, not the gaining of electrons. So answer C is incorrect. Let's check answer D. Answer D is when calcium loses 2 electrons to give calcium ions. Now with this, it is correct in the sense it is oxidization. However, it is not copper, it's calcium. Therefore, option D is incorrect. Option B, we have copper undergoing oxidization to form copper ions and 2 electrons. So clearly this is the correct answer because it is losing electrons and oxidization is losing electrons. Now let's move on to question 11. Question 11 is a calculations question, and it is a multiple choice question. So you have to get your correct answer and choose which answer is correct. A galvanic cell is set up containing a copper electrode in copper 2 sulfate solution connected to a nickel electrode in nickel sulfate solution. Calculate the EMF potential for this cell if standard conditions apply. Now with this question, first you would write out a shorthand notation of what the cell is going to look like. So for example, we would first have nickel, and we would have the nickel solution, which is the anolyte. And in the second cell, we would have copper, the copper catholyte, along with the copper metal here. So this is what our cell is going to look like. Now it says there's a reaction undergoing. So nickel is obviously going to undergo oxidation. That means it's going to lose electrons. So nickel will lose 2 electrons to form nickel cations. And then we have copper ions gaining electrons. Now you would work this out that nickel is undergoing oxidation because nickel is more reactive than copper, and that's in your standard potentials table. So this is what the equation is. Now if we look at it now, from your standard potentials table, you would realize that this is the nickel being more reactive than copper is the anode with a cell potential of that, and copper, the cathode, has a cell potential of that. So when you add these together or take away 0.35 from minus 0.26, you would add them, then you would get 0.6 volts, and that is the answer. So from here, option C gives us 0.6 volts. So therefore option C is the answer. There we go. And this is a good working out, but you don't need working out for multiple choice. You don't have to show it, but you would have to do it in order to get the answer. Now let's move on to question 12. Question 12 asks, what is a standard reduction potential? Now here you have to give the definition of a standard reduction potential. Standard reduction potential is a measure of the relative tendency of a substance to gain 1 or more electrons compared to the standard hydrogen half cell. Now it is important to first define it as well as include this part. Because it is a comparison of the standard hydrogen half cell, you have to always include that as well. So this is a good example of the definition. These are measured under standard conditions of 25 degrees Celsius, 1 atmospheric pressure, and using 1 moles per liter electrolyte solution. Now these are the conditions that you would have the standard reduction potential in, and this is also a vital component of your answer for such a question. Now let's go to question 13. Question 13 asks, identify the instrument used to measure the potential difference between two half cells. Now this is a pretty simple question, and also it says identify, which means you just name it. And what would you use to measure the potential difference between two half cells? You would use a voltmeter. And this wraps up our lesson, and we learned about EMF today, where you learn how to calculate EMF, as well as we learned how EMF works in reduction and oxidation reactions. Thank you.